Hello and welcome to this section of the Physics Tutor, and in this section we're going to cover the topic of capacitors with a dielectric. And just like with all sections in physics, when you read the title and you're like, wow, this is going to be really hard, but really it's a very, very simple concept. Basically what we've done up until this point, the last few sections talking about capacitors, we've introduced them as storage devices. It's a device where charge can go in, be temporarily stored, and then later on we'll learn that you can suck that charge out, and that lets you do lots of cool things with circuits. You can use them to generate oscillations, to kind of pull charge in and out. It creates oscillations. And so capacitors, they're used in every electronic device that we have. Pretty much anything that you can pull off the shelf has a capacitor in it somewhere. In this section, what we're going to do is expand on what we've learned from previous sections. So up until now, all of the capacitors that we've talked about a plate with a separation distance d and a surface area on the plates, right? So a surface area A, separation distance d, but we've always basically talked about there being air, basically an air gap between those plates, or maybe even a vacuum gap where there's nothing at all between there. And so everything's been derived up until that point. But in real life, most capacitors are not constructed with just air between them, or just a vacuum or something between them. I mean, you can certainly construct a capacitor to do that, and the first ones probably were. And you can go in the lab and build one like that. But all practical capacitors, the guys that you'll pull out of a computer if you slice them open, you're not going to see an air gap between there. You're going to see some other material in there. And that material has a fancy word. It's called a dielectric. All right, so don't get too wrapped up in the word. It just means material between the two plates of a capacitor. That's all it is. And you can put anything you want in there. You can put plastic in between the two plates. You could put glass in between the two plates. You could put an orange peel if you wanted to between the two plates. You can put anything you want as long as it doesn't really conduct electricity. You want it to be an insulator. You want the electric field to be able to run through that dielectric, but you don't want it to really conduct or short circuit that path. You want it to be an insulator. Now, why you might ask, why would you construct a capacitor with something in between the plates? And the answer is it raises the capacitance. And that's very important. So make sure you understand, when you put a dielectric in between two plates of a capacitor, it increases the capacitance. So I think you can all see immediately why that would be a useful thing to do. We build a capacitor with a certain geometry, surface plate area A, distance D, and we get a calculated capacitance for it. All we have to do now is take some styrofoam or some plastic or rubber or something, put it in between the plates, but don't change anything else, and now our capacitance has improved. And that's just because of what's going on at the atomic level with the electric field and how it's interacting with that material. It raises the capacitance. So in order to see how it raises the capacitance and to kind of calculate the results, let's go and talk about that right now. So recall from before, I shall say, the parallel plate capacitor with an air gap or a vacuum gap. And what we have learned before, really not telling you so explicitly, is that the capacitance is equal to the permittivity, epsilon naught, we called it, times the plate area A divided by the distance D. So the larger the larger the surface area of the plates are, the higher the capacitance is. Physically, the smaller the distance between the plates, if you get really, really close together, then that makes this number get really small, makes the whole thing get bigger, so the capacitance gets bigger. So two ways to raise the capacitance: increase the plate area or decrease the distance between them. All right, epsilon naught is the permittivity of free space. Remember, back in the very first part of the electricity and magnetism sequence, we talked about what is permittivity, and permittivity is just a natural constant that expresses sort of the properties in terms of electricity and magnetism, the properties of free space, meaning of vacuum, meaning no air molecules at all. But what we're going to find is that air is so closely behaved in terms of permittivity, so close to empty space that we really didn't have to make the distinction at all. But just for now, just remember the parallel plate capacitor is an empty space between it, characterized by this permittivity of free space, plate area, plate separation distance. All right, now if we put a dielectric between, BET is between the plates, what do we end up with? You can go and measure this in the lab, and what you will find is that the new capacitance, C nu, that's why I'm writing it there, is equal to kappa. It's very hard for me to write a nice looking kappa by hand, but that's kappa, times epsilon naught, which is the permittivity of free space, times A over D. So look at these two guys. They look almost exactly the same. We have permittivity of free space times the area divided by the distance, which is exactly what we have here. The only difference is we have a new guy out in front. So this guy, this term right here, this is the capacitance, we're just going to call it C air or C vacuum. The capacitance of this capacitor in air or in a vacuum. We'll talk a little bit more about why that's the case in a minute. This guy is what we call the dielectric constant. Dielectric constant. So basically, all the examples that I gave you a minute ago, rubber, air, or rubber, glass, plastic, anything non-conducting that you're going to put in between the plates of a capacitor, they're all going to have a different dielectric constant. So, and that constant is going to be greater than 1. And I'll show you a few values here in a second, but it's going to be greater than 1. So basically, since everything is the same, if you introduce a dielectric, the capacitance is going to go up, which is just what I told you in words a minute ago. So this equation is just telling you in words what we've already talked about. So let's generalize this a little bit more and say that, so in general, the new capacitance that you get when you introduce a dielectric is simply equal to this dielectric constant, we call it kappa here, times the dielectric of the capacitor if it were in air or if it were in a vacuum, because the capacitance when you have air between them and when you have a vacuum is almost exactly the same. So these are two really important results, and I'm going to try to help you remember that by putting a little guy around them like that. So when you put a dielectric in, you're raising the capacitance because this constant is different for every material that you put in there, and it's greater than 1. So let's give you a few examples. Examples of dielectric. Now, in your physics book, you can find pages and pages. If you go on the internet, you can find even more. So I'm not trying to give you an exhaustive, list of dielectrics. I'm just trying to give you a little, smattering so you can kind of get an idea. What if you had a vacuum, which is basically absolutely nothing? Well, in that case, this is the material. Let me go ahead and write a title heading here. This is the dielectric constant. And this I'm going to talk about in just a second. This is the dielectric strength over here. I'll talk about what that means in just a second. But if I have a vacuum, the dielectric constant is just defined to be exactly 1. It's a definition. There's absolutely no atoms there, so there's absolutely number 1 for the dielectric constant. The dielectric strength is infinity, and the unit of this, we're going to use for the purpose of this table, is kilovolts per millimeter. All right, so think about this for a second. If the dielectric constant of a vacuum is 1, then if I go up to my new and improved capacitor guy and stick a 1 in here for its dielectric constant, then the result I'm going to get is going to be the capacitor formula that we've been using all the way up until now. So it makes total sense. So the general capacitor equation to calculate capacitance is this. It's just that when you're dealing with a vacuum, you stick a 1 in here, and so it reduces to what we were using in the previous section. I'm going to come back to this in just a second. Don't worry too much about that. Let's look at air, because we've been talking about air a lot in terms of what's between the plates. What would be the dielectric constant of air? Right? Actually, just to make it clear, it's not the dielectric cost, it's the dielectric constant. That's what I'm trying to say here. What is the dielectric constant of air? If you measure in the lab, it'll be 1.0054. And it's dimensionless. It's not really a constant, so there's no dimensions here. The dielectric strength of air is 3, and the unit is the same, kilovolts per millimeter. All right, now I think we're to the point now where we can start to discuss more about what this table means. The dielectric constant of air is this number, which is very, very close to 1. So if we take this guy and stick it into our real and true equation for a capacitor, this is going to be, this K is 1.0054. which means that it slightly increases the capacitor above and beyond the capacitance it would have if it were in a vacuum. But it's very, very slight. If you take a capacitor and you put it in outer space where there's no atoms and you measure its capacitance, you're going to get a value. Now, if you take that capacitor and bring it back to Earth where there's air between the plates and measure its capacitance, the value is going to be very, very, very similar because this dielectric constant of air is so close to 1, right? Now I want to talk about, and that's why up until now, when we've been talking about capacitors and dielectrics, you know, we live on Earth, so we have an atmosphere here. So we've always been talking about all of our equations have epsilon naught. There's never any mention of this, because if you're measuring capacitance in a laboratory, it doesn't really matter much if there's air between the plates, is what I'm trying to say. If you're getting really accurate, yeah, you have to plan for it, but most of the time you don't. So that's why we don't worry so much about it. And so when you're dealing with air versus vacuum, you kind of just basically say the air's not there because it doesn't really much matter. All right, now I want to talk about this column before we fill out any more of this table. This is the dielectric strength. It's also called in your book the breakdown voltage of this dielectric. What it means is if I put material between this capacitor, it's going to behave exactly the way I expect it to behave, but if I increase the voltage, which is basically going to increase the electric field inside the capacitor, right? If I increase it more and more and more and more and more, eventually I'm going to get to a point where I'm going to destroy the capacitor. It's going to burn up. And that's called the breakdown voltage. So if I put, or the dielectric strength, if I put air between a capacitor, what this means is the dielectric strength of air is 3,000 volts, 3 kilovolts per millimeter. What that means is if I hold up a millimeter of air between my fingers, that means I can put 3,000 volts across this gap this big. If I put 3,001 volts, it's going to break down. And we'll talk about what that means in a second. So it's telling me how many volts, which is sort of basically telling you how much of electric field I can put on there without burning it up. Now, why does it burn up? It burns up, quote unquote. I'm using that as a word, but really what's happening is, don't forget, if you have an electric field there, if an electric field between my hand and this paper, you know, the arrow's going this way, what's happening to those atoms in the dielectric? The dielectric is right in the middle of that electric field. Well, that dielectric cannot conduct electricity very well, but it does have electrons orbiting all of those atoms inside the dielectric. So those electrons are going to tend to be, you know, pulled opposite of the electric field, and the positive protons in the nucleus are going to tend to be pushed along with the electric field. So if you can imagine an electric field going this way, and I have an atom here with electrons going around, the positive nucleus is going to gently be pushed in the direction of the electric field because of it's following the field lines. The electrons, which are negatively charged, are going to go the opposite way. They're going to tend to pull that atom apart. Literally, the electric field is tugging those electrons this way, pulling the nucleus this way. If you increase the electric field more and more and more and more and more and more and more, the force is going to get more and more and more, and eventually you're going to reach a point where those electrons are going to be ripped out of that atom, and it's just going to be ripped apart, and it's going to temporarily create a conducting path in there. And that's basically what you see with lightning. When you think about it, you've got clouds that's very charged. The air, as you can see, takes quite a bit of voltage to be able to break down air. But lightning does it because of so much charge built up in the clouds. And it builds up and it builds up and it builds up. Eventually, it ionizes the air, which means it rips the electrons right out of the orbitals. That creates a very temporary conducting path where that lightning can make it to the ground. And the same thing can happen inside of a capacitor. If you exceed the breakdown voltage, then that dielectric's basically going to burn up because the electron's going to come apart. It's going to create a conductor inside there because the electrons are free now. Electricity is going to go through it, it's going to heat it up, it's going to burn it up. And so literally it'll start smoking inside of your circuit is what will happen if you start to exceed that. So that's sort of a little bit of an aside. Let me get back to some more examples of dielectrics. Another common one is polystyrene. Polystyrene, that's an insulator. The dielectric constant of polystyrene is a respectable 2.6. And the breakdown voltage, or the dielectric strength of polystyrene, is 24 kilovolts per millimeter. That means I need 24,000 volts to break down polystyrene if I have a gap of it 1 millimeter across. All right, what else do I have? What about paper? Let's just take a sheet of paper. And believe it or not, you can make a capacitor with paper. What if you stick that between two plates of a capacitor? The dielectric strength will be 3.5. And the breakdown voltage will be 16 kilovolts per millimeter. It's still pretty respectable. And then finally, let me just give you one more example. What about Pyrex? What is Pyrex anyway? It's the stuff you use in the kitchen in your measuring cups. You put it in the microwave. It looks like glass, but it's not exactly glass. We call it Pyrex. The dielectric strength of Pyrex is 4.7, right? And it can withstand 14 kilovolts per millimeter. So what this means, this breakdown voltage, if I have a gap of 1 millimeter, then this Pyrex, let's say, can withstand 14,000 volts across that gap with no problem. If I increase the voltage, then I burn it up. But what if it's not one millimeter gap? What if it's 5 millimeter gap, right? Then it's physically farther apart. Well, this breakdown voltage is telling me how many thousand volts I can take per millimeter. So if I'm 2 millimeters apart, I'm going to double this voltage that it can take. If I'm 5 millimeters apart, physically wide, then I can take even more, 5 times the voltage across it. But there's a trade-off there, because if I make my capacitor really, really thick, right, so that I can withstand a big breakdown voltage, if I make my distance really thick, then my capacitance is going to go down. So you see, I have competing factors. I want my capacitor to be really, really small and really close so I get my capacitance high. But when I do that, I cannot take as much of a voltage across it. And that's sort of like a trade-off here. All right, so that's the general guy. The most important thing for you to know in this part is that the capacitance of a capacitor increases if you put a dielectric in there, and it increases because the dielectric constant that we have, we insert it in there and it increases the capacitance. Making it more simplified, we take the old capacitance that we had in air or equivalently vacuum, and we multiply it by this multiplier there. We also talked about the breakdown voltage, ripping apart the electrons and basically rendering the atom sort of like a little conductor, and that's why it kind of burns it up. So if we want to look at this in general, right now we've been talking about capacitors. We said, hey, you can multiply it by this dielectric constant. And if I just stopped, you might say, well, okay, that applies to capacitors. It actually turns out that the whole idea of multiplying times a dielectric constant in terms of this capacitor and the way that you just multiply it like that, it actually applies to any equation that you learn in electricity and magnetism that has an epsilon naught in there. Let me show you what I mean by that. If we have, let me just write down a few things. In free space, which is vacuum, we use the following. So if we have, any sort of equation, we use the following thing. We use the permittivity that we use in our equations, we just call it epsilon naught, which is the permittivity of free space because we're in free space. All right? So for instance, for example, we have Gauss's law, which we used extensively. Gauss's law, don't forget, was epsilon naught times the circular integral of the electric field dotted with dA is equal to the charge enclosed inside of the Gaussian surface. We did tons of problems with Gauss's law, but we always used this form. And the reason we always used it with epsilon naught out here is because we were always sort of thinking in our head when we did all those problems that we were always doing those experiments in a laboratory on Earth or in deep space, in free space. Now we've learned that the air, the fact that when you introduce air, the dielectric constant of air is so close to 1 that it doesn't really affect anything if you just use the permittivity of free space here. Because the fact that you're in air, it just doesn't change things too much. So if you're doing an experiment in a laboratory on the ground, it's probably okay just to use this, even though this really and truly applies only if you're in deep space when there's no air in the way. All right, but in general, to kind of open your eyes a little bit, in general, let me try to write an L properly, not free space. In general, what we really do is we say, instead of the permittivity being epsilon naught, we in general say the permittivity of the substance is equal to this dielectric constant times the permittivity of free space. So in other words, the permittivity is modified by this dielectric constant depending on where we are. So if we're doing our experiment inside of air, then theoretically we would modify the permittivity by this constant. It just so happens air is so close to vacuum it doesn't really matter. But let's say we were doing this experiment inside of a piece of plastic. I mean, maybe we literally have a block of plastic and we put an antenna in there and we just start doing an experiment. Well, the permittivity is different. So you would modify all of your equations by taking epsilon naught and sticking this dielectric constant out in front. And in fact, this applies where, in general, for any equation that we're dealing with in electricity and magnetism, you would just modify it accordingly. So, for example, Gauss's law revisited in this case would be, if we're doing it inside of a piece of plastic, for instance, it would be dielectric constant times epsilon naught times the circular integral of E dot dA is equal to Q enclosed. I really want you to stare at this until you really make sure you understand. Because what this is basically saying is that if you're in free space, there's no atmosphere or anything, the permittivity that you use in all of your equations, capacitors, Gauss's law, anything I can throw at you, is always going to have epsilon naught. If you're doing your experiments not in space, which is always the case, you're always going to be on Earth, or you're always going to be underwater, or you're always going to be inside of an antenna chamber or something like that, then the permittivity that you use in all of your equations, not just for capacitors, all of your equations, including Gauss's law, right, is just going to be the same equation that you used before, modified by this dielectric constant. And furthermore, I'll tell you, in most introductory physics books, they use the letter kappa to tell you this dielectric constant. But when you get into more advanced text, maybe engineering text, then it's really usually written like this. Epsilon is equal to epsilon r times epsilon naught. So instead of K, sometimes you might see it written as epsilon r. This is what we call the relative permittivity. This is called a permittivity of free space. It's the same thing. It's a dielectric constant. There's no difference. It's just a label. I'm just telling you that in some books you might see epsilon r. It kind of reads a little better if you think about it too, because if you have a plastic or something, you might think of it having a relative permittivity relative to free space. That would be some number, and then you're just using that number to modify the normal permittivity of free space. So I guess what I'm just trying to say, if your book has kappa, if your book has whatever, it's the same concept, but in a lot of engineering books, when you get on down the road, you call it epsilon r, relative permittivity. Okay, and in fact, when would you might use this? You might use it for capacitance, right? We've talked about this, but when else would you might use something like modifying Gauss's law to calculate something? Best example I can think of is your cable company, right? You've all looked at a coax cable, right? Comes out of your wall, goes into your television. That's actually called a waveguide. I know it sounds really complicated, but it's really a waveguide. The signal is coming down, it's being transmitted, you've got a copper electrically conducting, cylinder, and in the middle you've got that single wire. That's the other terminal. But if you cut it in half, if you actually got a hacksaw and cut it and looked at it, you would see the outer conductor, and then you would see the inner conductor. That's that central wire, and then you would see some white stuff that's filling the gap, right? The white stuff is used to give it structural support, but the white stuff is, drum roll, it's a dielectric, okay? You could figure out what that dielectric is, and you would be able to ascribe a number to it, and then all of your equations that you would use to calculate the waves going in there, whatever you're doing, you would all be modifying epsilon naught with that relative permittivity or that dielectric constant out in front of it. So that's something I just wanted to give you a practical example of, because it's something that's in your house. You may not even realize you had a waveguide in your own home, right? But you do. So let's do a problem and try to flex our muscles a little bit on this. All right, let's say you have a 7.4 picofarad capacitor, but you need to convert it so that this capacitor stores 7.4 microjoules of energy with a maximum potential difference of 625 volts. Which dielectric should we use to fill the air gap, right? So that's a very common question. They'll give you some information, and then they'll tell you that you want to change the capacitance or you want to change something, and you have to select a dielectric. What you need to do is write down everything that you know, and so that you can make some progress. So I always advise to draw a picture. So first you have a regular capacitor with an air gap, right? And this capacitor is 7.4 picofarads. That's just given to us straight up in the problem. So write that down. And it says we want to modify it. So basically we want to create a new capacitor with some dielectric in the center, right? That's this guy right here. And we want to store energy into it. It doesn't give us the capacitance. It says that we want to store energy of 7.4 microjoules. The unit is joules, so it's energy. So it's not giving us the new capacitance, it's giving us some energy that we want to store into this capacitor. It says that we want this potential difference to be 625 volts. 625 volts. All right, so that's what we have to work with. Now, a lot of times, people try to get to the answer in their head. How can I do this and figure out what dielectric I need? It's basically going to be impossible for you to solve these problems in your head. That's my advice. So just write down what you know. You know that the new capacitance, after you put the dielectric in there, is going to be equal to some dielectric constant. This is what you want to find, times the old, or the air-filled. You know, I could even write it that way. I could put it times the air-filled capacitance, right? I don't know what the new capacitance is, because we were not given that, but I do know what the old capacitance is. It's 7.4 picofarads, but don't forget that's 10 to the minus 12, and that's farads, so I'll just leave it like that. So this is one equation that I sort of have. Now, what can I learn from this side? This is basically all I can do with this. All I know is I'm going to put something in there, it's going to increase the capacitance, I don't know anything else. But on the other side, I have quite a bit of additional information. I know that once I'm done inserting this dielectric, this new guy is going to store energy. And I don't know what the new capacitance is, but I do know what the new energy is going to be. The energy storage in any capacitor is 1/2 times its capacitance. In this case, it's the new capacitance, because we put the dielectric in there, times the voltage squared, 1/2 CV squared. We've used that in the last section. So the energy stored is going to be 7.4 times 10 to the minus 6. That's on the left-hand side. On the right-hand side, I have 1/2, right? And I have this new capacitance here, which is going to be kappa times 7.4 times 10 to the minus 12, like this, okay? To make that a little more clear, 7.4 times 10 to the minus 12, like that. But don't forget, I have v squared, so I'm also multiplying by v squared, 625 squared. So make sure you understand what I have. This is the energy that I want to store. This is 1/2. The new capacitance is what I wrote down here. This times this, and then I have the voltage squared. Okay? So look, I don't have anything else in here except numbers, numbers, numbers. I have this guy. So I can solve this equation. It wasn't so apparent initially, but I can. So whenever I take this guy, I'm going to have 7.4 times 10 to the minus 6 is equal to, and on the right-hand side, I'm going to have kappa, K, or the dielectric constant, times, when I take 1/2 times this squared, I'm going to get 1.57 times 10 to the minus 6. And so the dielectric constant, when you divide these numbers out, is going to be 4.70. So this is the dielectric constant. If I go over here, the dielectric constant of Pyrex is 4.7. And the breakdown voltage of Pyrex is 14,000 volts per millimeter. Okay, so if I go back to my problem, basically that allows me to basically just circle the answer and say, okay, I need Pyrex. And that's the answer, right? Now, we're only putting 625 volts across this capacitor. Pyrex can take 14,000 volts per millimeter, so it's incredibly unlikely. It's basically impossible you're going to exceed that breakdown voltage. So this is the answer. You're going to be choosing Pyrex. Now, it's one of those guys that when you're first working it, you don't really know exactly how to proceed because you're given some information here, you're given some information here. If you try to figure it all in your head, it's going to be difficult. Write down the fact that the new capacitor is just a increase over the old one like this, write down what you know about the energy stored, plug it in, and then you realize at this point you say, aha, I can solve that. But if you try to move too fast in your head, then you're going to run into a brick wall eventually because you're not going to be able to see all the way to the end of the problem. The next problem, a parallel plate capacitor that's air-filled has a capacitance of 50 picofarads. If the plates, and this is a multi-part problem, the first part says, if the plates have a separation of 0.35 square meters, what is the plate separation? And the second part says, if I fill the gap, right, that has air in it, with a dielectric of K is equal to 5.6, that's a dielectric constant, what's the new capacitance? So basically I have an old capacitor and a new capacitor, I'm just asked slightly different things about them. So the first thing is, for part A, what I'm trying to find is what is the plate separation? But it's parallel plate capacitor, so I know that if it's air filled, it's going to be the capacitance is epsilon naught times the surface area divided by the distance between them. That's the equation for parallel plate. It's air filled, so technically, yeah, there's a kappa out in front with a slightly different number, but I'm telling you, for all of your problems, it's okay just to use epsilon naught when it's air because it's so close. So let's plug in the numbers that we have. The capacitance is 50 picofarads. 50 times 10 times 10 to the minus 12 is equal to, on the right-hand side, epsilon naught is just a constant 8.85 times 10 to the minus 12. And then A over D. A, the surface area we're given is 0.35 meters, 0.35. And D is given by this. So kind of a simple problem. We've sort of done problems like this in the last section. But all we have to do now is really solve for D. So what we have on the left is 50 times 10 to the minus 12. On the right, we multiply these two things together. We're going to get 3.1 times 10 to the minus 12 over D. All right, so then the next step, we'll just move D over here by multiplying. 50 times 10 to the minus 12 times D is equal to 3.1 times 10 to the minus 12. And so we just divide by this guy here. Then the plate separation D is going to be 0.062 meters, which is fine to leave it like that, but if you wanted to shift the decimal 2 places, that would be 6.2 centimeters. And this is the answer. That was the answer for part A. What's the plate separation? Part B says, if I fill the air region, the air gap, right, with a dielectric of K 5.6, what is the new capacitance? What's the new capacitance? Well, don't forget that the new capacitance is just simply equal to the dielectric constant times the capacitance in air, or vacuum. We're counting them as the same thing. So what we're going to have here is 5.6. What was the capacitance in air? That was given to us in the problem, 50 picofarads. 50 times 10 to the minus 12. So this is very, very simple. We're just taking the original capacitance, multiplying by the dielectric constant. So the new capacitance is simply 2.8 times 10 to the minus 10, and the units here, as I'm dealing in pure units, is farads, and if you wanted to be a little bit better about it, you'd write it in terms of, either picofarads or microfarads. And so if you take this guy and move it 2 units to the right, you would have 280 times 10 to the minus 12, which is picofarads. There's many ways you can leave it. You can leave it like this if you want. You can write it in terms of nanofarads, picofarads, whatever you want. I just choose to shift it 2 spots to the right, so I'll get 10 to the minus 12, so I'll get picofarads. So you see, not a hard problem, but you have to know it. You have to, all of physics is like this. You have to know what you're doing. In this case, realizing that that number one, air gap is the same as vacuum gap as far as our calculations go. Secondly, you're just modifying and calculating a new capacitance, which is basically increasing it by a factor of, in this case, 5.6. So there's not a lot of complicated math here, but it is something you have to understand the concepts for if you have any hope of success. So here we've had a good introduction to taking a capacitor and increasing its capacitance by putting a dielectric in there. We've done a few simple problems just showing you how it's really done, how to use the ideas and the concepts. Just like anything else in math and science, it's always easy once you understand how it's done. After that, it's like, what's the big deal if it's introduced to you in the right way? So I hope I was able to do that here. Done a couple of simpler problems. In the next section, we're going to continue working some problems with different dielectrics and capacitors. We're going to get into some problems that take a little bit more math to solve, but basically the fundamental idea is what you already understand, which is you're taking that capacitor, sticking something in between the air gap, that increases its capacitance, and so we're going to exploit that in the next few sections there. I'm Jason with MathTutorDVD.com. I hope you've understood this section. Make sure you understand it. Go into the next section on additional problems with dielectrics and a capacitor, and we'll understand how to do these slightly more complicated problems.